So welcome back, everybody. And today we should be able to have a TV which is more stable, because we can actually use an additional gadget here, so we don't need to use the HDMI cable. Okay, so what we are going to do today, after a quick repetition of what we did yesterday with plain gradient descent, which is the simplest possible method you can apply, we are going to look at modifications of that. And the modifications we are going to look at involve first something which is called gradient descent with momentum. Has any one of you heard of that? That's a very simple, quick recipe where we can bring in information about previous iterations in case the gradients vary a lot. And then we can dampen these variations. This is a method which actually converges pretty fast. Often you need only half the number of iterations to converge to the final result. So this is a quick fix which we can add to the codes. Then we are going to look at this famous method like adaptive gradient, where we are going to train this learning rate. And then ADA-grad is the first we're going to meet. There's something which is called root mean square propagation. And then we have the famous ADA method. And these are the methods we are going to discuss. And you can apply these irrespective of whether you do plain brute force gradient descent, where you calculate the gradient with all points you have, or if you do a stochastic gradient descent. So what we discuss now are just technicalities for the gradient optimization. And you may sound, many people actually surprised when they hear about all this gradient optimization part, because this is really the bottleneck of all of machine learning, because we have to optimize. And when we come to neural networks next week, then you will see that this becomes even more important, because then you will have millions of parameters you need to optimize. And that means that you need something which is fast and reliable. So you want to have a method where you don't need to spend too many floating point operations and still get a reasonable result. What is reasonable is actually you who have to decide what is reasonable based on your experience. So yesterday, we looked at this first simple example where we just put up some kind of vanilla data, and then we calculated the gradients. We set up the design matrix. So this is just a repetition of what we did. We had the function here when we just had a linear fit. If we have more than a linear fit, you obviously get beta 2 times x I squared, etc., etc. This is just the simplest possible thing we can do, a linear fit. And then we calculated the derivatives, and this is something which we can write in a more compact way like this. And this is the gradient we want to drive to 0. So here are the individual gradients, the derivative with respect to beta 0, and the derivative here with respect to beta 1. And this is the way you would write it in a more compact matrix vector notation. And then we could also calculate this Hessian matrix. And the thing which is nice and which makes life much, much simpler for us with ordinary least squares is that the Hessian matrix does not depend on the unknown parameters beta, which we want to optimize. This is not the case normally, which means that this calculation of the Hessian matrix, which we can do here outside any iterations, is something which we normally cannot do. And every time we iterate one of these parameters beta, so if you do a neural network, you will have millions of these. So you can just think of the operations of a million lines here of this type. And then you do, let's say, 100 to 1,000 iterations, which means you do 1,000,000 times 1,000, just to give you an example of operations. And every time you would have to invert this matrix. You don't want to do that, period. Because then your matrix would be 1,000,000 times 1,000,000. And you don't want to calculate all these derivatives at every single step. And that's why we normally replace this with this gamma. And everything which rotates around gradient methods deals with ways to have information about the gradients for this quantity here. So you can update it for every iteration. There is a lot of research going on, and there's a whole topic which is called natural gradients. So if you search for natural gradients in the literature, this is a very active field of research. And as I said yesterday, if you want many new friends and friends which will cite you, this is actually, it sounds extremely simple and stupid. I mean, why? I mean, just this gamma here, right? And what we did in order to use Newton's method was to Taylor expand the function we want to optimize just to the second derivative and just leaving out the rest. And there's no guarantee that higher derivatives may be small. So there are lots of approximations, and it's important that we know these approximations. Because when you use software like TensorFlow, PyTorch, and so on, the learning rate is a parameter you have to set. And people who use this as black boxes, they say, okay, I just fix the learning parameter to this and this. And then people ask them, what does the learning parameter mean? Yeah, maybe I may not know properly. And it's just a parameter. So for us, it's very important to actually understand what's going on. I think that's important. And the examples here, which we went through yesterday, are pretty simple ones. We could invert the matrix. In this specific case, we have the exact result from standard ordinary least squares. And we found then that if we tune this learning rate to be very, very small, as we said yesterday, we would not converge properly. And if we made it too large, we would just go totally astray, and we would not get a reasonable result. So one thing I just wanted to show you here is just this summary where we ended yesterday. So these gradient descent methods, they treat all directions in parameter space in a uniform way. And it can take also an exponential time to escape saddle points, even if you have random initializations. So it's extremely sensitive to the initial condition. Now, before we move on with momentum, so momentum is a way to speed up the convergence, because if you do a gradient descent, convergence can be slow. As you see here, you have the same learning rate in every direction. So there's no information about the gradient of one of the parameters, which can adjust this learning rate. So let's just look at a very simple example before we move on. And let's switch to the whiteboard, because then I wanted to introduce a simple trick, which is called gradient descent with momentum, which is extremely simple to implement. And this is something you should implement when you do gradient descent methods. So let's just take a quick look at it. And what we can look at now is a simple example. Oops, not that one. So one of the things which we said yesterday is that the function which we want to optimize is, and x now is a vector, is something which we could write as a second order function in terms of this unknown quantity x minus some x of t times b. That's the function. This is essentially what we are setting up when we Taylor expand the cost function to second order. And this A is actually our Hessian matrix. And this X is these unknown parameters beta. Okay, so let's look at a simple example. Let's suppose now that X, and when this is the thing which often is irritating when you read textbooks in statistics about machine learning, is that you would find statements like this. You should guess from the context whether this is a vector or scalar or matrix. This can actually be frustrating because sometimes it's not so clear. So X is now a vector. When I don't, so I should put it more boldface here. So that has components X1 and X2. Let's assume that. And now I'm defining a function. So instead of writing X, I now write it in terms of the two variables X1 and X2. And this is something which we could write out as 1/2. And then I have X1, X2, and this is obviously transposed. And let's assume that the matrix looks like this, 2, 1, 1, and then 0. And then I have multiplied with X1, X2. And I have a minus, and then I have my vector B. So I can take the transpose. This is a scalar. So I take the vector B, which is just 5 and 3, transpose, times X1, X2. And if I write this out, this is just a function which looks like X1 squared plus 1/2. So it's actually 1/2. No, not 1/2. not that one, it's actually x1. x1, when you just perform the matrix vector multiplications, plus 10 x2 squared minus 5x1 minus 3 times x2. So what I've done is actually to write out a function like that. And now I want to find the optimal x1 and x2. So what I'm going to do then is simply to take the derivative of this function with respect to x1, and I want that one to be 0. And this shouldn't be a surprise. This gives us x2 times x1 plus x2 minus 5. And then I take the derivative of dx2, and this should give us x1 plus 20 x2 minus 3. And when I collect these ones, then I have just two equations with two unknowns. I hope you don't get offended if I present cases like that. Then what I get is x1 is 97 divided by 39, and x2 is equal to 1 divided by 39, which is close to 0.026, and this one is close to 2.49. So that's the solution. When we now want to find the optimal parameters, x1 and x2. So this, what you see here, is the same as we did with the linear approximation, that the linear fit to the data, which we had previously. We had parameters beta 0 and beta 1. So in the previous case, what we saw on the slides, we had beta 0 and beta 1. So it's basically, it's the same. And the kind of function which you have here is the one you will always see when you look into any textbook on convex optimization problems. These are the typical quadratic functions which are presented in these textbooks. And then the assumption is that this matrix A is normally a semi-positive definite matrix, which means that you have a convex optimization problem. Now, when you now do the iterations here, what we could do, now the assumption is obviously that f of some guess x0. So you could now start with a guess where you say that x0, this is a random guess. You would typically start with a random guess for the solution. And then the hope is that this is larger than the next one, and larger than the next one. And then finally, there is an x optimal, which I write this hat, which is where we have the minimum. Okay? And then when we set up the iterations here, what we would have then would be an x1, the first iteration, which, I just put an x, I should put this not like that, but I should have an x0 like that. So that means that x1 for one of these components, whether it's a component 1 or component 2 here, so let's just write this as an I, and I can be either 1 or 2 here. This is given by x of I, and the term which we have, so this is the first iteration we would do, and this contains now a gamma 0 multiplied with the derivative of the function evaluated at x0. So let's just do that. Be careful a little bit with the indices here. So this is x of I. This is the process which we will start with. And then this continues, so that means that we end up with a recipe for these parameters where we have I plus 1, and that's given by the previous value of I minus gamma of I, and then we have a derivative with respect to this specific parameter. So I should have put a k here, sorry, k, and then we have a iteration k here. Yeah, that's perfect.
If you can just 1 moment
to
check the cable for
the TV. This is much better.
Okay. And this works?
Yeah. Okay. Because the cable was a little bit unstable.
Indeed. This is what
was. Yeah.
But
No, sorry.
I didn't know what you were doing.
Yeah. Yeah. Yeah, the cable was a little bit unstable. Yeah. 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 No, that's fine. Thank you. Yeah. Thanks. So essentially, the process we are doing is this kind of iteration. And if you now look at a graphical presentation of this, you could now think of the way these parameters develop. So we would have x1 and x2 here. And then we started with, so if I'm making a drawing here, and you will see that my drawing skills are very limited. Actually, if I go beyond one dimension, I'm just at loss. And according to my wife and my daughter, I just live in one dimension. So when I try to do something in 2 dimensions, then it's getting tricky. So we had a -3. So we started here, -3, and then no, -3, and then we had 1. Sorry, we can take away that one, and also take away this one. So we have a -2 here, and then we have a -4 here, -3, -2, and then this goes up to +4 here. And the final solution, so we start with a -3 for x1, and then 1 for x. So let me just redo it, this one. So we have a 0 here. So we start here. This is our point x0. No, not there. I cannot draw even. Here, that's where we start. -3 and 0. So this is our guess, x0. And then what may happen is that we go to the next one, which could be here, x1. And then this continues up and down. And then we have the final value, which is here, which is -2.5 and 0 point something for y, x2. So we could have something which slowly migrates towards this point, iteration after iteration. So this is something which we could do now if we run with just a fixed learning rate. So we can adjust this learning rate so that this process converges faster. So the standard gradient descent has the same weight in all directions, and it's not a very fast thing to implement. It's fast to implement, easy to implement, but it may not converge quickly. So the simple change to that is something which is called gradient descent with momentum. So let me show you how that functions, because that's very easy to implement. So that's the first thing which we should implement when we run these calculations. And I will try to tell you why this is called momentum. This is historical. And I like to call this gradient descent with memory, because you keep a memory of previous iterations. But let's look at the way this was historically introduced. And what you could think of now is Newton's equation of motion. And if we look at that one, and you have some kind of damping or friction term, so you have the equation of motion here, of the acceleration, and then you have a drag or friction term, which is velocity dependent, dx dt, and then there is some kind of external force. Let's just assume that. And this external force is the gradient of the potential. Okay? So we know that the force is the negative of the gradient of the potential. And if we discretize these equations, and this is an equation which we will use a little bit later when we also discuss automatic differentiation. So the standard way to solve these equations is to discretize. So that means that the second derivative, which we have, dx dt, is normally approximated with a formula where you Taylor expand x around x plus a step delta t and x minus delta t. You add the two, and then all the odd powers of delta t cancel. And then you get only expressions with the even powers. So this is an equation by which you can calculate the second derivative. So this would be given by a t plus delta t and this is probably a formula which you have seen many times. It's actually, again, 2 Taylor expansions minus 2 times x of t divided by the step delta t squared. And I'm going to rewrite this in a more compact way as x of t plus delta t plus x of t minus delta t minus 2x of t divided by delta t squared. Have you seen this formula before? Yeah. So this is just you taking the Taylor expansion of x of t plus delta t and x of t minus delta t. And when you add these 2 Taylor expansions, all the odd powers of delta t disappear due to the minus sign in front of one of them. And then you can get an approximation for the second derivative. And then we know that the first derivative, if we just stay with Euler's forward stepping, this is something which we can approximate with x of t plus delta t minus x of t divided by delta t. And then we can plug this in back into the equation and then reorder the equations. And then you will see how we can actually split the equations in 2 terms, one which is an update, which depends on the previous step, and on one which then defines the next step. So let's look at this equation here. And so we plug it in, so we have m, and this is the approximation to the second derivative, delta t plus x of t minus delta t minus 2x of t, and this is divided by delta t squared. And I have plus mu of x of t plus delta t minus x of t divided by delta t. And this is given by, and now we're putting equality signs, although these are approximations. So this is just now the approximation to the equation here. And then I define 2 new quantities. So I define a delta x of t plus delta t, which is simply x of t plus delta t minus x of t. And then I define a new quantity, delta x of t, which is given by x of t minus x of t minus delta t. And then I can now rewrite my equation in the following way. So I can isolate this delta x t plus delta t. I can rewrite everything in the following way. And this is equal, so I multiply out this minus delta t squared. So I have a minus delta t squared divided by the mass plus mu of delta t times delta v. Sorry. And then I have plus this m divided by m plus mu of delta t. This is just a rewrite of my equations. But pay attention now that this delta x of t contains now an information about a step before. And this is the whole thing with this momentum here. And what you normally do next is you define a new parameter. So we would take this parameter, which you see here, this one, and simply relabel that one. We call that for delta, nothing but that. And then I have a new parameter, which I'm going to call for gamma, this one. So I just call this parameter for gamma. And then what I can do then is to rewrite my delta x of t plus delta t in terms of this parameter minus gamma. And here I have the gradient. And then there's a gradient of v of x. So you see now this is starting to look like the standard gradient descent approach, which we had. We have a gradient multiplied with a parameter gamma, which plays the role of a learning rate. But then I have something which I call plus delta times delta x of t. So keep in mind now that when we look at the old thing we did, is that this quantity here is actually x of t minus x of t minus delta t. So as a parenthesis, think back at what we did as a beta of I plus 1, which is equal to a beta of I minus some learning rate, which I now call for eta, times the gradient, which in our case was the gradient of the cost function of C of beta of I. Okay? So if you look at the similarities here, what you see now is that this term here would play the same role as this one. This term here, however, has now parts of information from this one and also the new step. So it's slightly different. And then there is a term here, which we now have, which has a parameter delta and contains information about the previous step. So the inspiration comes from setting up these equations. So if I now change my x of t and I let that stand for beta of I, the previous iteration, and then what I'm going to do now is to let x of t plus delta t, I'm going to replace that one with the old beta of I plus 1. And then my delta v, which I have here, is now going to replace my delta c of beta of I, which is the same as this function g of beta of I, or just g, the gradient as we defined it. Okay. So what we have then is an iteration now, which we can rewrite as follows. So we can have a beta of I plus 1 is equal to beta of I, and then minus, and then I have this parameter eta, which is now going to play the same role as this gamma, but just another name for it. And this is multiplied with the gradient. And I just leave it like this. I just drop this beta of I term. And then there is a new term here, which goes like plus delta. And then I have my beta of I minus my beta of I minus 1. So this term here becomes a constant. And this constant which you see here is a constant which now is normally a hyperparameter. So this is a constant which we can tune. Now, the whole idea here is that if your gradient varies a lot from one step to the next one, if you then have information from a previous step, then you would average out the strong variation when you move from one step to the next one. So if you go back to this figure which we had here, suppose now here that it varies a lot when we go up here and up there and down here. But if I now keep information about this step, when I move from here to here, that can smooth out the strong variations. And this smoothing out is something which normally gives you a quicker convergence. And typically this parameter, which we have here, this parameter eta, this parameter delta is something which you would tune. But people often put a weight of 30% on the previous iteration, which means that you have a certain information about what happened before. And typically this parameter delta is something which takes values between 0 and 1. And a typical value is something like 0.5. And if you go back to the way we defined it, if you look at this delta here, when you then let this mass or this parameter mu here go to infinity, then this is just going to be dominated by this parameter mu delta t with a fixed mass, which means you go to 0. If you make mu very small, then it's m divided by m, and then it's equal to 1. So it takes, if you think of this relation which I have here, it's a parameter which switches between 0 and 1. So this is the historical, analogy, which was introduced many, many years ago. Many people use this just as a trick, and they call it memory parameter because you keep a memory about a previous iteration. And if you guys are running, has any one of you done Hartree-Fock calculation or density functional theory? So these are iterative, yeah? You will. Right. So in Hartree-Fock theory, you will often have a parameter delta where you keep information about the iteration before, because sometimes the solution can vary a lot, and then you dampen the big variations. And you will see that often there's a parameter which is put to 0.3 or 0.5, and you may ask, where does this come from? This is actually the same recipe which is used in all these kind of iterative algorithms. And it's the simplest possible you can think of. So the algorithm here, and this is something which we would always do. So it requires a learning rate, quiet learning rate. So you need to fix that one. And we call this one, in this case, eta or gamma. You can choose which one you want. And you require a momentum parameter. So it's normally called momentum parameter. I will use memory because I like that better. And you would require that one, delta. Then you require an initial value. This is a random guess often. Initial value for beta. And also the initial value for the, in this case, a parameter you're updating. Let's call this parameter v of I and v of I, or just let's call it v. So the algorithm itself is while stopping criterion not reached. So this is the while loop we're setting up. And the first thing is to compute the gradient, g, for a given iteration. And I'm skipping this I for the iteration number, because that's implicit here now. And then I would then compute, because people would call this the velocity update. Compute so-called velocity. V is often used as a velocity here. So what we do then is that we compute a v of I, which is actually equal to this parameter delta of beta of I minus, oh, let me just be a little bit more careful with the way I put the things here. So I have a beta of I minus beta of I minus 1, the previous value. And then we call this a minus a learning rate eta multiplied with the gradient. And then we apply the update. Which is then beta of I plus 1, which is now equal to beta of I plus this parameter v of I. Sorry, v of I here. So this is just an intermediate step which you calculate. And the reason why it's called velocity is if you go back to the equations we did for this update of the position, there is a velocity dependent term, which is then just given by these terms which you see here. So you will often see in the literature that this is called the velocity term. But this is nothing but just a way to rewrite the equations where you now have an information about the previous iteration. And then you compute the update. And then this is end y. So this is a pretty simple algorithm to implement. And let's just see some examples of it. So in the slides here, you will actually, if we go back to the Jupyter notebook here, you will find some examples. So let's go back to that. Where did I have? Okay. That one. Nope. I think did my Jupyter notebook stop? Okay, let me just go back here. No, here we were. Here we were. So that's the one I wanted to share. No, not that one. Why doesn't that one come up? This one. Nope. Okay, let me just do one thing here because that should So those of you online cannot see this one. So let me just take away this one. And let me just restart everything. I didn't want to share the right screen here, so let's just do that one. And then start the screen sharing. Okay, now you should be able to, those of you online should be able to see the screen again. So let's do that. I think the people online cannot see the screen here. Exit full screen. Okay, there was something wrong with my full screen option here. Okay, so let's, sorry for this small inconvenience here. And let's now just go down to the discussion of adding momentum to the standard brute force gradient descent. And if you scroll down here, there is an implementation of it. And this function here, and again, I hope you don't get offended. This is an x squared with a derivative equal to obviously 2 times x. So you can see now that I have done the difficult task of calculating the derivatives. And in this case, we just do a plain gradient descent, as we did before. And we know that the minimum has to be at 0. As I said, I hope you don't get offended if I have such simple cases. If I run this now and plot the results, what you will see now, these are the function values at the different, so this is the initial value. And we know that 0 should be, when the function is equal to 0, is down here. So this was done with a given learning rate, a constant learning rate. And you see now that I needed, from the start here, I needed something like 30 iterations to get this close to 0, roughly 30 iterations. Now I can repeat the same thing with just adding momentum. So the algorithm which I described now, if I rerun it, you will now see that in my case here, after roughly 13 iterations, the function is 0. So this is something which speeds up my calculations with a factor of 2. And in this specific case, what I've done now is simply to have a momentum factor of 0.3. So many people would play around with that. And this is simply a cheap way of actually updating your gradients. And since it works so well, you should always do that. Not do a plain gradient descent, but do a gradient descent with momentum. So now there are ways we can improve these calculations by changing the learning rate. So in this specific case, we kept the learning rate fixed. And there are many simple recipes by which we can set up a change of the learning rate. So there's a very simple one. You start with a given value, and then you multiply that with an exponential, and then you let it decay exponentially. So that means you start with 10 to the minus 2, and then you let it decay exponentially, so it becomes smaller and smaller. So you start with a given value, and then you let this be updated as you move on, till it reaches a very, very small value after some iterations. That means that you start with, let's say, 10 to the minus 2, and then you end up with 10 to the minus 4. Then you can start with another value, 10 to the minus 3. So typically you would have a grid search of our values where you can now have an exponential decay. You can keep it constant, or you can have other types of updates. And I'm going to show you the simplest brute force updates you can make. Then, after we're done with that, we are going to go over to ways where we can bake in information about the gradients. And one of these methods is called adaptive gradient, which is shortened to ADAGRAD, which works very well for convex functions. and then we have root mean square propagation, and then finally we have Adam. So I just wanted to present these methods, and you can use these methods irrespective of whether you're doing a stochastic gradient descent or you're doing just a plain gradient descent. So these are just techniques to update the learning rate. So let's look at some of the, before we take a small break, so let's look at some of the very simplest ways by which we can update the learning rate. And you will encounter these recipes in many, many different applications. So what we might call as the cheap recipes for updating the learning rates. So if we now look at this learning rate, which we have put up, so one way is actually just to keep it constant and choose a grid of values. So that means that you would run calculations for different learning rates and choose a grid of values. So you would run calculations. Suppose now that eta is put to 10 to the minus 5, and then you run a new calculation with 10 to the minus 4, 10 to the minus 3, etc., to some kind of final value. Obviously, you should not have it larger than 1, because you want this to actually be smaller than 1. Because typically larger than 1 will mean that you will have huge steps you're jumping around with. And then the standard way of doing this is then to make a grid search. You can interpolate between the values and try to find the optimal values. So this is one brute force way of doing it. And you will see that in many applications. And it's cheaper to do that than to calculate the Hessian. So it sounds strange, but it's actually cheaper to actually run these calculations than to update with the second derivative. So this is a simple brute force way. Then we have, as I mentioned, we have an exponential decay. That's another way of doing it. And these are all cheap ways of updating it. So one is exponential decay, which we'll also encounter. So that means that you will have an eta of k, which is given by some eta 0. And then there is an exponential here, and minus, and then some parameter of k. And then this has a parameter here of eta of k minus 1 typically. And this k parameter can then be given by some specific value which you choose. And k here, which you have, could be the number of iterations. Number of iterations which you have. That is pretty common. There is something which is called a linear one. And if you look up in the literature, you will find many such, what I normally call cheap recipes. These are not used very much. What people nowadays use is algorithms like Adam, root mean square propagation, and Adagraph. But you see, these are pretty easy ways of implementing things. So you could have a eta of k here, which is given by some 1 minus some alpha, where alpha is a parameter. And then you have an eta 0, the value you start with. So eta 0 could be, for instance, this value 10 to the minus 4. So you make a grid of values, and then you start iterating. And then for every iteration, you change the values. And then there would be some plus, some alpha, and this is then multiplied with a parameter, which is normally called gamma of tau, where gamma of tau is a new parameter. So this alpha is typically given by some iteration number, k, and then divided by another constant. So where this is divided by a constant which you specify. And this gamma of tau is also constant. And normally this this eta of tau is normally set to something like 1 divided by 100 times eta 0. So there are tons of such approaches which you can use. You can have alpha as just a constant, which you fix. You can let this alpha change as a function of number of iterations, etc., etc., etc. So these are what I call cheap recipes or poor scientist recipes, which are easy to implement. And the whole idea is that you start with a given value, which we call eta 0. You set up a grid here, and then you let the value diminish. So it moves. So if you start with 10 to the minus 3, it moves to 10 to the minus 4, or another value. And then people would pick the value for the, let's say, the mean squared error, which is the lowest one. Or if you're doing a classification, the best accuracy you can get with that specific learning rate as initial value. There are lots of recipes here. There's something which is called a randomized grid search. There are optimizations of this grid search. And then behind that one, you can use these cheap ways of doing that. Or, as we will see after a small break now, is a better way of doing that. And that is AdaGrad. That's the first one we're going to encounter. And then we have a root mean square propagation, which is also widely used. And then you will find Adam. So as I said, these methods can be implemented without the stochastic gradient descent. So you can do a plain gradient descent, or you can do a stochastic gradient descent. The stochastic gradient descent is something we will also discuss after the break here. So these are the methods you see here. These are some of the most used ones in the machine learning literature. And in particular, this method here, Adam, is the most used one. And you will often see in scientific articles, we used Adam, or root mean square propagation, for the update of the learning rate. I hope you don't find this too disappointing, because in a way, it takes away the kind of magic behind deep learning, right? Because suddenly we just have to tweak all these parameters. And I hope you also see that this is to strike this kind of balance between the number of floating point operations you want to use when you're updating the second derivatives and the accuracy you want. And the whole thing, when you run a machine learning algorithm, is that you can see that as a numerical experiment. That's the kind of approach you should take to machine learning. So when you're setting up a neural network, you would play around with different options for the number of hidden layers, nodes, the architecture in terms of activation functions, etc., etc., etc. And then you would run it with many of these parameters and then pick the results which give you the best answer. And sometimes you will see that people say, well, we used that plain gradient descent because that gave the best result. And there is no more, how to say, intuition beyond that. Because you often have complicated multidimensional objects you want to optimize. And we don't even know what the plot looks like because it's too complicated to plot. Should we take a small break? Is that okay with everybody? Let's do 10 minutes now. Right? Is that okay? Because we began a little bit later, but let's just do 10 minutes now because I wanted to go through some more stuff here. So what I will be doing now is actually to jump a little bit back and forth in the notes. So last lecture, we ended with the naming of AdaGrad, root mean square propagation, and Adam as methods to update this learning rate. Now, before we do that, I actually wanted to say something about automatic differentiation before we actually go more into the details. So what I'm going to present you now is an intermediate step. And this is an extremely helpful tool, which I strongly recommend to use when you're dealing with derivatives of complicated functions. And this project is actually a numerical project, which I think is one of the most beautiful numerical algorithms, because it allows us to calculate derivatives almost to numerical precision by repeated usage of the chain rule. So today, since the focus is on this ways to update the learning rate, I will not give you the mathematics of automatic differentiation. That comes next week. Is that okay? So now you can think of automatic differentiation as something which cures all problems with derivatives. And let's keep automatic differentiation as a kind of black box now. And what I'm showing you is how you can use it in your Python programs. And you can actually use that if you program in C++ or Fortran. Julia, is somebody programming in Julia? C++? So C++ is called autodiff. And automatic differentiation is the repeated usage of the chain rule on known functions. So when we are setting up the cost function, this is often a function defined in terms of well-known functions, x squared, x cubed, exponential of something, it's log of something, etc. So we have functions which we have at the basis. And then it's the usage repeatedly of the chain rule. There are two ways of setting up the derivatives. One which is called forward mode, which I will explain to you next week, and one which is called reverse mode. Reverse mode is nothing than the back propagation algorithm in neural networks. This is something which is not communicated well in the machine learning community. And we will come back to that, I promise. So now just bear with me in the sense that I'm just going to present you how you can use AutoGrad as a library, okay? And it is not symbolic differentiation. If you use, for instance, Mathematica or SymPy, have you used symbolic Python? So SymPy has the feature that you can write a C++ code or Python code based on the analytical expressions for the derivatives. However, when it writes the analytical expression for the derivatives, this may not be an efficient equation to, or an efficient code to compute the derivatives. So automatic differentiation is actually much, much better. And I will show you examples of that next week when we start discussing neural networks. And then hopefully you will see more of the beauty of automatic differentiation. And it is not, if you think back to the equation we had before the break, of a finite difference scheme for the second derivative, that is a highly inefficient way of calculating higher derivatives. So if I take this finite difference for the second derivative I had before the break, when we demonstrated momentum with a gradient descent, if I use that formula and calculate higher derivatives based on that one, even for a simple function like e to the x, I will get wrong results. So it's nothing about this, and it allows you to calculate derivatives to numerical precision. So take the following function, which you see here, f of x, which is given by this function here, and this is the analytical derivative. Now, this analytical derivative, as you can see, contains many operations. As we will see next week, we can actually reduce this calculation to fewer operations than the analytical expression, which is also interesting. And AutoGrad here is something you would now, you have an element-wise gradient, and you would simply import that one from AutoGrad in terms of this function egrad. You have the function you want to calculate here, and you have the analytical expression. I'm setting up an array with 1,000 points. And here I simply calculate the gradient of that function, or the derivative, by using AutoGrad. And then I compare the two, and what you will see then is that basically there's no difference. And you see the difference between the analytical one and the one calculated by AutoGrad, which is 10 to the power of minus 15, which is 0 computational. So AutoGrad is something I strongly recommend. Now, AutoGrad is not a project which is continued anymore, and it has been in Python replaced by JAX, J-A-X, and I will show you examples of that later. So JAX also includes high efficient just-in-time compilation. It contains vectorization and parallelization, and that really speeds up your Python codes. So that's something which I would strongly recommend to use later. Now, there are several examples here, and I'm going to go back now to, I'm going down here, and I'm going to set up the calculation of ordinary least squares with AutoGrad, just to show you how easily you now can calculate the derivatives. So this is my cost function. This is the mean squared error. This is the same example we had before, this kind of a simple vanilla function, first order polynomial. And now I'm just defining my function here, which is a function of this beta. And I want to take the derivative with respect to beta. And then using autograd, what I'm doing now is simply to set training gradient is equal to the gradient of this cost function. So I don't need to set up the gradient manually by taking the matrix X transpose times X times the vector beta minus X transpose times Y. So the only thing I do now, just one line of code. This is extremely powerful because if you look at here, when you change cost function, the only thing you need to do now is just to set up a list of different cost functions. And then you can make a class with many different cost functions. And then you can change around instead of you setting up all the derivatives by hand. What you do now is simply that you use autograd like this, just one line. And then you specify which cost function you're using. That's extremely powerful and it saves you a lot of time. And it gives you much more flexibility when you code. I hope you see the simplicity here. And actually, if you're calculating derivatives numerically and your functions are defined in terms of simple analytical functions like polynomials, sine functions, cosines, exponentials, logs, etc., use automatic differentiation. I mean, don't hesitate, just use it. It's something which really simplifies the structure of a program. Just ask me, because I've been calculating derivatives for many, many years. And when you code it, it's so easy to interchange some indices. It took me a month to find an error because I had interchange indices. And if I had used autograd, I would have used that month for something more meaningful. So I had derivatives of matrices, and I simply had done a stupid error with an I, which should have been a J, which is so easy to do. Have you done such errors before? Yeah. I can see that. This is a common experience. So if you look at the function here, basically what I'm going to get is the same result as I had before. So it doesn't change. And I've also added momentum. This is the way I actually repeating some of the examples. And you can see now I'm using automatic differentiation here. But now I'm plugging in the momentum. And the reason why I do that is I just wanted to repeat how easy it's actually to bake it in. So the gradients here, and theta is my parameter beta, which we had previously. I just called it another name. And I have this momentum parameter, which is 0.3 here. And this is the new change which I take. This is the eta times the gradient plus this delta times change, which is the previous value plus the new one. And then I update theta with just this minus the new change. And then the change is the new change, and that keeps being iterated here. If I run this code with and without momentum, you can look at some of the output now. So in this specific case, you can see the problem which pertains to this function here. I'm setting 30 iterations. So my gradients are not zero yet with 30 iterations. So keep that in mind. And if you look at the first case, which is now done with a favorable learning rate, this is plain gradient descent with a automatic differentiation. And these are the two gradients, the derivative of beta 0 and the derivative of beta 1. And you see that they are, after 30 iterations, one is 10 to the minus 2, and the other is also 10 to the minus 2. Ideally, we want them to have equal 0. I would need more iterations then. If I use momentum, you see now that after actually 2-3 iterations, I have a value which is almost the same. So when I use momentum, when I've done 30 iterations, I have 10 to the minus 4. So you see how much more efficient gradient descent with momentum is. So, and it's so simple to implement by simply introducing this parameter, which we have here, this momentum parameter. You have the change, taking into account the previous result, and then you get a new change, and then you update the parameter here. So that is extremely simple to implement, and you should do that. Now, what I'm going to present to you here now is first using Newton's method, because in this simple case, I can calculate the Hessian. So if I use Newton's method with the Hessian, because the Hessian in this case with two parameters is just a 2 by 2 matrix. So I have the second derivative with respect to beta 0, with respect to beta 1, and then the cross terms with beta 0 and beta 1. And then I can invert it, so you can see now I calculate the Hessian here, and then I calculate the inverse of the Hessian. And since that does not depend on the unknown parameters, because this is standard ordinary least squares, I now calculate the gradients, and the only thing I do now, I do my iterations, and then I calculate my inverse times the gradients. So that's a matrix of dimension 2 times 2 times a vector of length 2. So that gives me the parameters of length 2. I have two unknown parameters, beta 0 and beta 1. So if I do that with Newton's method, you see now that my gradients, this is my first guess. I just have a value, I guess, and which gives me a bad value. But then after that, I have 0. So one iteration with a random guess. So clearly, if you can calculate the Hessian matrix, or you have what's called quasi-Newton methods, which allow you to calculate an estimate of the Hessian matrix, you should try to do that, because they are much, much faster. And you see the result here, the gradient is 0. So life, however, is not that nice. As we know, there are always complications. And the systems we are going to look at and the type of machine learning algorithms imply that we have millions of parameters. And then to calculate the Hessian is not possible. But if you can do it, if you have a case like the Wisconsin cancer data, where you have something like 30 features, then you would have a matrix of dimensionality 30 times 30. And then you can allow yourself to calculate the Hessian, because that's not a big matrix to calculate and invert. So that's fully possible. But if you do a normal neural network case, we can just forget, unfortunately. So I'm going to, as I said, I'm going to jump a little bit, but what I wanted to introduce to you first are actually these methods, which are called adaptive gradient and root mean square propagation and Adams. So these are the methods which you will encounter in the machine learning literature, which people use routinely. And AdaGrad is one of these methods. And what you have then is that first you start, they call the learning rate epsilon. You have some initial parameter theta, which we call beta or theta in the programs. I have to be a little bit more consistent here. Then there is a small constant which is included in order to avoid division by 0. So the way it runs now is that you start with a while loop. You sample, and we are coming back to this. It doesn't need to be a mini batch. You can actually apply this to a standard gradient descent. So I'm coming back to these mini batches here. But then you would calculate, you find a set of data, you would find the corresponding targets, you compute the gradients. But then, instead of using this simple way to update the learning rate, you calculate something which is called a squared gradient. So this is without the Hessian matrix. So this is a component by component multiplication. It's called a Hadamard multiplication. So you update this parameter R, which is the sum of the gradients. And then you compute an update for the learning rate, where you now, instead of having the learning rate, as you had previously, you have this delta, which is set to 10 to the minus 8, 10 to the minus 7, in case this R is 0. And then you simply update the square root of that one. So that means that the learning rate gets updated with information about the gradient. This is AdaGrad. It's another cheap method of doing it instead of calculating. So everything you see here is done in order to avoid calculating the Hessian. But now you have information about the gradient. So this is one of the most used methods, adagram. And when you have updated the new learning rate, you simply add that one to the previous value, and then you get the new value. That sound okay? So this is just a recipe which people have cooked up and which works. And there are examples here. And in this specific case, I'm actually setting up with stochastic gradient descent, and we come back to that. I have a second order polynomial. There is no noise, so I should get 2, 3, and 4 as my parameters if I make a good fit here. And you can see now that my method here, and this has stochastic gradient descent, which I will come back to. That gives me, so these are the values which I get by plain linear regression, standard ordinary least squares. And then I get a theta value, which is basically the same, but now this has a stochastic gradient descent. So I won't get exactly the same due to the stochasticity. I'm coming back to that. And if I can add the momentum as is done in this case here. But you also have root mean square propagation, which is another algorithm. So these are all algorithms which update the learning rate by using information about the gradients. So again here, you now define the parameter delta. You have this small constant in the denominator here, which is used to avoid division by 0. But now you have something which is called a decay rate. So it's a way to let the learning rate decay from a starting value. So here you accumulate again the squared gradient, but you keep now an information here about previous values, which is multiplied by this rho. So you have this rho here times the new value, and then you have a 1 minus a rho here, and then you have the same expressions which you had in adagrad. So the only difference from adagrad and root mean square propagation is this new parameter. And then you calculate the same update of the learning rate with this value r, and then you update the value. So this is root mean square propagation. But now you have an additional parameter. And then in this specific case here, I'm actually using the method with a specific value for rho, which is 0.99. This is my initial learning rate. You can obviously change that one, and you can see the dependence on that one. So in this case, you see now that with root mean square propagation, I'm also getting with a stochastic gradient descent, I'm actually getting a result which is basically very close to what I get by standard matrix inversion with ordinary least squares. Now, in this case, I'm now setting up this term. This is the gradient first, and then I have this new term here, which is the gradient times the gradient. So this is row-wise multiplication or Hadamard multiplication. And then I take the gradient only, the diagonal only, and I invert this quantity here. And then I have my update. So this is root mean square propagation. And the methods which you see here obviously depend on your choice of the learning rate. So if I were to choose this one very small now, the learning rate, then you would see that this doesn't converge because the learning rate is too small. So all these methods, they start with a learning rate, and then you update it now with information about the gradients. So in the previous case, which we had on the whiteboard before we took the break, we looked at very simple ways of just changing the learning rate without information about the gradients. Now we're actually baking in some kind of information without calculating this ratio we had yesterday, where we had the norm or the gradients divided by the gradients times the Hessian matrix times the gradient. That would be the steepest descent way of doing it. So we don't involve the Hessian matrix, but we actually have only the gradients, which we use to update the gradients, the learning rate by taking this epsilon, the original learning rate, and divide it by this parameter, which now scales the learning rate, and then multiply it with the gradient again. So these figures are actually taken from the textbook of Goodfellow et al. In their chapter 8. and that contains a very extensive discussion of all these optimization methods. So I invite you to take a look at these optimization methods there, and that's chapter 8 of the textbook of Goodfellow et al. So I don't know if you looked into that textbook. I strongly recommend to take a look at it. So if you just go to deep learning, so this book is, you can download chapter by chapter, and chapter 8 here is the one which contains a pretty good discussion of different optimization methods. And also chapter 4 discusses a lot of these topics about numerical computations. So I recommend that you can download chapter by chapter. I think even the whole PDF is online. You can probably find it. And then what we have next, the final method, is Adam, and this is the one which is most used in the literature. So this case combines the adaptive gradient with momentum update. But now it introduces two parameters. And I actually have to confess that I always have to rethink why this works. So what you do now, you have to define two new parameters, which take values between 0 and 1. And they have tuned them to 0.9 and 0.999. So I don't remember exactly how the tuning was done. So you would initialize these momentum variables S and R. You calculate the gradients. You update the biased first momentum, which now contains information about the gradient multiplied with this rho 1. You have the second momentum, and then you correct this bias by taking the value S and divide by 1 minus this rho 1. And then you have to the power of the number of iterations, T, which is here. And then similarly with this R, and then this R is now given by this value R divided by this second momentum. And this is the way you update now the learning rate. And then you apply the final update here. And Adam is often a method which really works best. And here you will find an example of a code which I wrote. So in this specific case, you see now that you're, with even stochastic gradient descent, you're basically spot on. So Adam is often a method you will see in the literature, which is simply, people will simply say we used Adam because that was the one which gave the best result. The article itself, as I mentioned, is something which has more than 150,000 citations. So it is one of the most standard methods for updating the learning rate. Yeah, here are the examples with JAX. So the thing I wanted to end with now is a discussion of a stochastic gradient descent, because that's something which is included in all these codes, but I haven't explained it to you, and why we would do stochastic gradient descent. So let's go back a little bit in the slides. I'm jumping a little bit back and forth here. So if we move back and beyond this automatic differentiation case, I just wanted to say a little bit about the gradient descent method. So gradient descent, as we saw, is a method which, one, can be very slow. It may need lots of iterations, and it also calculates the full gradient. So if we have a matrix X, which has dimension n times n, and n is equal to 1,000, to perform a matrix-matrix multiplication with the same dimensionality requires 10, so n cubed floating point operation. So if you have a matrix which has 1,000 elements, it means 10 to the power of 3. You cube it, then you're doing 1 billion floating point operations. So when you then calculate the gradients, you're actually doing all these floating point operations to calculate it in every iteration. So let's just bring up and let me try to motivate a little bit what this gradient descent is and why we would do it. So let's just bring up the whiteboard again. So I showed you through the slides, ADA-GRAD, root mean square propagation, and ADAM, the way you implement these algorithms. But let's now look at the one of the algorithms which is normally used, and that is stochastic gradient descent. Suppose now that you have a function and you want to calculate and find the optimum for that specific function. So typically what you would do now, if you have a function like this, something like that, suppose you have this one-dimensional function and this is your f of x. So when we start with Newton's method, we would start with an initial guess. So if our initial guess is here, if this is our x0, then we are basically in a region where we have a saddle point. So when we calculate the gradient after some few iterations, we may actually just be stuck here. And then we won't move anymore. Alternatively, if we start here randomly with x0 as a guess, then we may move down here and then just be stuck here. So the way we start sampling is very important. So the standard gradient descent is very sensitive to that. Similarly, we would love to start here with an x0, and that would bring us down after some few steps down here. And this is where we would like to be. So this would be a local minimum. This is a saddle point. And this is an unwanted, very much unwanted situation. We can be happy with a local minimum, but ideally we would like to reach the global minimum. So stochastic gradient descent is a way where we actually going to sample these different starting points in a stochastic way. And then we are going to repeat the calculations again and again. So you can think of this as a statistical calculation of the gradient. So that's one way of thinking why we do stochastic gradient descent. And the standard approach now is to do the following. So that is to split the data in so-called mini batches. So suppose you have 100 data points. This is the total number of data points which we have, 100. And then you could split everything into m equal 10 so-called mini batches. This means the following, that every mini batch here has 10 points. So every mini batch has little m equal to n divided by m points. So in this specific case, we have only 10 points. So that means that you would calculate the gradient now for the mini batches, every gradient, and then you would collect them. So the total gradient would now just be the sum over all the mini batch gradients. So a specific gradient for delta B here would now simply be 1 over m, the little m which we have, and that runs from I equal 1 up to little m. So this is a delta batch, a given one, m. And then we would calculate this cost function, or the gradient actually, the delta, as a function of the points which we have in here, which are now given by these mini batches. The way we would pick this point is randomly. So we can then pick a random index for where we start calculating the gradient. So suppose your data points span from x0 up to x99, since we have these points. And then we would have up to x9 is one batch, and then obviously the next ones and so on. So we would now pick an index randomly, so we could place ourselves in, so this would be batch 1, this would be batch 2, etc. So we could pick randomly batch number 3. And that means we would place ourselves here, and then we would calculate the gradient based on only this type of contributions. And then we pick the other ones randomly. So that would be one measurement of the gradient. And then when we've done this for all the data points we have, then we would repeat it again and again. And so you would repeat this operation when we are summing up this gradient, repeat a given number of times, And this number of times is normally called the number of epochs. And that would give us the final gradient. So in a way, what we are doing now is we are placing ourselves randomly in the space of observations we have. And then placing ourselves randomly, we then compute the gradient. Now you can do that with replacement or without replacement. And that's actually a big discussion in the literature, whether we should do that. I'm coming back to this. I just want to show you how we can implement this easily numerically. There is another advantage by doing this. So if you now look at this operation which we are doing, suppose that we have a slightly bigger matrix. Suppose now that n is equal to 1,000. And then we are doing ordinary least squares. And in ordinary least squares, the gradient is actually proportional to this x transpose times x multiplied with the parameter beta. And then it contains minus x transpose times y. So if we are doing this operation now, and let us assume that x, just for simplicity, is a matrix of dimensionality n times n. So what happens then is that if we look at this one, that requires a number of floating point operations, flops, which is proportional to n cubed, which in our case is equal to 10 to the 9 operations. So every time we are updating the parameters, we are performing this matrix multiplication. And that is a lot of floating point operations. If I now reduce this into smaller batches, so suppose now that a batch has only 10 points. 10 points here. And that means that I have split it into 100 batches because I have 1,000 points. And that means I have 100 batches and each one has 10 points. So if I then do these operations in that specific case, what I have is a matrix x times t for a mini batch. Requires only 10 squared to the power of 3 operations. So that's 100 to the power 10 to the power of 3. So this is roughly 1,000 floating point operations. And then I have 100 batches. So what we're doing then, and then we repeat this. So this will be one epoch, this 100 times. So that will be one run. So that means that I have 10 to the power of 2 times 10 to the power of 3, which is 10 to the 5 floating point operations. So this is a considerable saving in number of floating point operations. Instead, if I do it in a brute force way, and I take all the points I have and calculate the gradient, this is much, much more expensive. So the whole idea with these mini batches is actually that you reduce the number of floating point operations. But then we keep repeating this again and again as a function of the number of floating of so-called epochs. So let me go back to the slides and discuss this a little bit more by looking at the gradient, the implementations of the algorithm here. So in stochastic gradient descent, then what you would be doing, so the underlying ideas from the stochastic gradient descent is that we can rewrite then the gradients as a sum over a given number of gradients where you have a set of so-called mini batches. So as I said, you have a mini batch M, and in total there will be N divided by M mini batches. And that means that each batch, which is labeled by beta of K, contains now a certain number of points. So if you look at the case here, if you have 10 data points, and then you choose to have 5 mini batches, then each one will contain, if you now organize them sequentially, but you can organize them randomly if you want to. So you have X1, X2, up to X9 and X10. And if you have M equal 1, then you have all the data points, and then you're back to where you were. And the idea now is to approximate the gradient by replacing the sum of all data points with the sum of the data points in one of the mini batches picked at random in each gradient descent step here. So that means that you calculate now the gradient as a sum over all these different batches. And a gradient descent step would look like this, where you now have a sum over the mini batches. And where this K, which you have in K is picked I is picked randomly with an equal probability from 1 to N divided by M here. So let's look at a simple example a little bit down here. Let me just show you how you could implement this. I'm just going down here a little bit because it's just, so what you would do now is that a run over all the mini batches N here is something which you would now initialize here by finding the random index. And this is the total number of, if we now look at this, is the size of a mini batch. And the number of mini batches is the total number of data divided by M. In this specific case, I have defined N, the total number of points, to be 100. So if I divide that by 5 here, I have 20 points in each batch. And then here I have a simple update of the learning rate. So there is no ADA-grad, there is no root mean square propagation, just a simple update. And now I place myself randomly. I find the random index. And you see now that I calculate the gradient for these random starting value and random final value. So this is for X and this is for Y. And this is the gradient calculated for the mean squared error, which I'm hard coding now. There is no automatic differentiation. And then I update now my learning schedule. So I have an update for the learning rate. I could have kept this to be just a constant learning rate, but now I have a very simple linear way to approach to update the learning rate. And then I have my now updated parameters here. And in this specific case, what I'm doing is to place myself randomly, which means I'm doing random selection with replacement. So I could actually pick the same points again. And this is something which is a discussion in the literature. And in the above code, you use replacement in setting up the mini batches. And if you follow this link here, there's actually quite a discussion on whether you should do that or not. And then when you make these runs, you would run over a number of epochs. So that becomes another parameter. So your stochastic gradient descent will depend on the number of batches you specify, and also the number of times you just repeat these calculations. So you have to think now of calculating the gradient as calculating a statistical average of the gradient, where you rerun these experiments again and again. But each calculation here of the gradient is much cheaper than running with a full gradient with all the data points, which you would do in a gradient descent. So there is always a balance with how many epochs you run here, because suddenly this can become a large number. And you would have to fine-tune the stability of the calculation of the gradient as a function of number of epochs and the number of batches. So the whole thing now is that you place yourself randomly in the space of the data points you have. and then you calculate a specific contribution to the gradient. You sum this up, and that defines one calculation, and then you repeat this again and again. And the whole idea is you accumulate these expressions, and they should then at the end represent the gradient. But then with you having been allowed to start this in many, many different random positions. And hopefully then, avoiding you being stuck in a local minimum or a saddle point. So these are some of the hopes we have by using a stochastic gradient descent. So there is the hope that you can avoid a global, local minimum or saddle point, and two, that you actually reduce the number of floating point operations in calculating the total gradients. So these are some of the basic, overarching messages which pertain to stochastic gradient descent. And if we now go back to the functions which we had here, if we go down a little bit towards the end of the slides, you will see many implementations of stochastic gradient descent. So if we look at, for instance, stochastic gradient descent with AdaGrad, so what you would have then is now using AutoGrad. So this is the standard ordinary least squares, but let's take AdaGrad, which should be this one. No, that's the same code with momentum gradient. But let's do, this should be AdaGrad, yeah. So here I'm using automatic differentiation, as you can see. I import AutoGrad. I'm setting up my cost function, which now doesn't include the factor 1 of n, because I'm including that explicitly when I calculate the derivatives of the mini batches. I have 1,000 points. I have a simple polynomial. I do a standard ordinary least squares, matrix inversion. And now I define 50 epochs. This is a number you can play around with. It becomes a parameter. So in order to test methods for different functions, you will also have to play around with the number of epochs, the number of times you calculate these mini batches. I define the number of epochs here. I have an initial value for the parameters theta. And then I run over the number of epochs here. I update my learning rate using adaptive gradient. I place myself randomly in the position of all elements in the design matrix and then in the output. And then I just run the code here. And then you see that I'm getting pretty close to the exact value. This is a stochastic gradient descent. This result will, however, depend on the number of epochs. So I can obviously increase that one. So I could do 1,000, and I could have perhaps a larger number of mini batches and see what happens then. And now you see it's taking more time, right? Because I increased the number of epochs. And it didn't increase so much the quality either. So there is always this trade-off which you have to strike. So how many calculations do you want to do? And how long are you, what kind of precision are you asking for? So it's not given that if you increase the number of epochs that you will get a better result. And you saw that in the previous case where I just had 50, we can reduce this to 100 and let's see what happens. Now it was much faster. And I'm also getting a result which is pretty close. But we are calculating averages of the gradient, which means that you will not get the exact gradient. Just keep that in mind. And this works better when the system has many, many degrees of freedom or many parameters. So this kind of averaging works better when you have huge spaces of parameters. When you have few parameters, I would not use a stochastic gradient descent. Then I would just use a plain gradient descent with the calculation of the Hessian matrix. But as soon as you get into many parameters like you would have in neural networks, then you have to think of simplifying your calculations. So in this case here, if I now were to replace this with a standard gradient descent and AdaGrad, I would actually be spot on here. And if I were to use Newton's method and calculate the Hessian matrix, there is nothing which can compete with Newton's method here. when you calculate the Hessian matrix. So you, in a way, have to strike this balance. If you have less than 100 parameters, I would use either the calculation of the Hessian matrix or some quasi-Newton method and actually try to calculate the Hessian matrix. But as soon as you are in the thousands of parameters, this becomes numerically inefficient. And that's where people typically would use stochastic gradient descent. So this kind of balance is something you need to strike when you're implementing your codes. And as I said, the bottleneck of all these optimization algorithms, the bottleneck is how you update this learning rate. So it sounds too simple, but it's actually the harsh reality we have to live with when we deal with this machine learning method. So what I know that some of you have to go now for other lectures, but I was thinking that we could stay on. We take a small break now, and then we can discuss the projects a little bit more. And I sent you this email with the examples. And if you have time to think of it, we can just keep discussing that among ourselves. And if you probably have many other questions as well. So my thought now is that we just sit here and can discuss if you want, if you have time to. Else, next week, I will begin with neural networks, which will be the second part of the course here. So I will stop the recording for those of you online.